Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed how we can convert any system of linear equations into a differential and a signal flow graph. And we have solved this problem based on the equations. We can uh, kind of like set the arrows, and thereby you have discussed the elements of signal flow graph, which I have already discussed in the last class. So let us convert the given block diagram into a signal flow graph so that we can simplify the overall transfer function. So let us see how we can do that. So if we have a block diagram element of summing point, we can represent that as a node in which, based on the direction of flow of these signals, we can have the direction of flow of these signals same in the same manner as in the block diagram. And if we have two, which are one is a summing point and other is a node, based on that direction and direction of motion of the signal, we can have a signal flow graph. We can have two nodes. So I mean, a summing point in a block diagram can corresponding to a node in signal flow graph, and a node in signal flow graph is corresponding to a node in block diagram corresponding to a node in signal flow graph. Here, that is how we can convert. And if we have encountered a block of gain g of s, we can have uh, we could have converted that into a path and a branch of gain g of s. So we have, if you have a block, we can have a path gain, which is of gain g of s. And if we have a takeoff point over here, so this takeoff point can also be converted into a node with the following flow of signal. And if we have a takeoff point here, and after that we have a summing point, then we can represent that takeoff point as a node and this summing point as other node. And based on the flow of the signal, same as the flow of the signal in block diagram, we can represent the flow of these signals in signal flow graph. This is how we can convert the signal flow graph into our block diagram. And after converting the signal flow graph into a block diagram, how we can find the effective transfer function, which is the ratio of this output to input Laplace transform. How we do that? So for doing that, we have a formula which is called as Mason's gain formula. So this overall transfer function is given by Cs over Rs, which is nothing but summation over k pk del k by delta. So where k is the number of forward path and pk is the kth forward path gain, and delta is the determinant of this overall signal flow graph that is computed by 1 minus the summation of the loop gains plus summation of non-touching loop gains 2 taken 2 and minus some and so on, so on, like that. And del k, this is the isolated determinant. If we isolate this kth forward path, then we can have that similar kind of formula. But here the isolated, based on isolated forward path, we can find out this determinant. So we can, in this manner, we can find out based on this Mason's gain formula, we can find the overall transfer function of a given system. So in the next class, we'll be discussing how we do that, and based on the problem, that will be much more clear to you. So thank you guys. Thank you for your time. If you like the channel, please do subscribe to our channel, and please do share with your friends so that they will also get benefit from this channel. So thank you guys. Thank you for your time.